Okay, let's learn about our third method of approximating integrals, definite integrals, and that's Simpson's rule. So let's set it up. With the midpoint rule, we were estimating areas of regions using rectangles. So in a sense, we approximated a curve with piecewise defined function. Okay. Um, these functions were really step functions. So these are step functions. In other words, they involved horizontal lines. Horizontal lines. Okay. In the trapezoidal rule, we also used piecewise functions, but we didn't just use horizontal lines. We used piecewise linear functions, but these lines could be non-horizontal. Non-horizontal lines. Okay. Now with Simpson's rule, we're going to do something similar, but pretty radically different. With Simpson's rule, we're going to approximate a curve with piecewise defined functions as well, but it's going to be a piecewise quadratic function. A quadratic function basically means we're going to be working with parabolas. Okay. And when we partition our interval of integration, we need to partition it into an even number of subintervals. Let's take a look at our picture over here. Okay, so what you'll see with our picture here is, in this particular case on the left, we basically have two, we sort of have two rectangles over here, or two intervals, two subintervals over here. And in this case, my n is equal to 2. In the example on the right over here, we have 1, 2, 3, 4 partitions. So we have 4 pieces there. Our n is equal to 4. And you might be wondering, why is it important that we have an even number of subintervals? Well, the reason why we need an even number of subintervals is we really need 3 endpoints to fit a parabola. In other words, your parabola in general looks like y is equal to ax squared plus bx plus c. And you need 3 points to uniquely determine a parabola. So you need 2 unique points to determine a line. For a parabola, you need 3 unique points. So when we have 2 subintervals, that allows us to have 3 endpoints over here. And once I specify this endpoint, and this endpoint, there's only one parabola that's going to fit through those endpoints there. Okay. So if you looked at our second picture on the right over here, we have 3 endpoints. The orange curve describes the parabola, the unique parabola that goes through those 3 points. And we can approximate the area under our curve using the areas under parabolas. So let's take a look at what our formula is going to look like. I am going to remind you that we had discussed Sn was how we would label our approximation for Simpson's rule. And we're going to have the width of each subinterval delta x, but this time we're going to divide it by 3. And we're going to multiply by, let me write down the function values first, and then I'll write the coefficients next. So we're going to have f of x0 plus, let's leave a little bit of room, f of x1 plus, leave a little bit of room, f of x2, and then that will be enough for us to describe the pattern. I'll describe the pattern in a second, and then the last endpoint will be f of xn like this. Okay. So what should those coefficients in front of the function values be? Well, the first one is going to be a 1, and then it's going to be, the next one's going to be a 4, and then a 2, and then it keeps alternating 4, 2, 4, 2, 4, 2. So keeps alternating 4, 2, 4, 2, so on and so forth, until you get the very last guy. The very last guy is just going to be a 1. Okay, so just to reiterate, you're going to take the width of a subinterval and divide it by 3 this time. You have your function values evaluated at each of those endpoints, and then the coefficients are going to alternate. The coefficients on the first coefficient and the last coefficient are going to be 1, and then it's going to alternate 4, 2, 4, 2, 4, 2 in the middle. Just as before, our delta x is going to be b minus a, the length of the region of integration, all divided by n. And we really need to be able to bound our error in order to know what how accurate our approximation is going to be. So we're going to label our error as E sub s for Simpson's rule. We're going to bound the absolute value of the error. So we're bounding the overestimate and the underestimate amount. Just as before, we need to bound our derivative. In this case, it's the fourth derivative. So our fourth derivative is bounded by k. And our error bound has a factor of k in there. It's going to be k times b minus a to the 5th power divided by 180 times n to the 4th. All right. So this is our error bound for Simpson's rule. All right, everyone. Take care.